our universe hides a profound and elegant secret. For over a century, a ghost has haunted the equations of physics, a particle that should exist but has never been seen. It is called the magnetic monopole, a solitary north or south pole wandering alone, and its absence is one of science's most stubborn mysteries. By the end of this journey, you will understand not just one, but 25 distinct reasons why this phantom particle shakes the foundations of everything we know, from the quantum world to the fate of the cosmos. We will see how its elusive nature threatens our grandest theories of unification, how it might be hiding in plain sight within strange crystals, and why finding just one could rewrite the rules of reality itself. What does it feel like to chase a ghost that the universe seems determined to hide? The story of our missing ghost begins not with a complex particle accelerator, but with a set of 4 deceptively simple equations written in ink on paper. In the 1860s, the Scottish physicist James Clerk Maxwell performed a feat of intellectual unification. He took everything humanity knew about electricity and magnetism, 2 forces that seemed distinct, and wove them together into a single, elegant tapestry of mathematics. His equations described how electric charges create electric fields and how moving charges, or currents, create magnetic fields. They predicted light itself was an electromagnetic wave, a revelation that reshaped science. But within this beautiful symmetry, a curious and glaring asymmetry was baked right into the foundation. The equations treat electricity and magnetism as 2 sides of the same coin, yet one side of that coin appears to be missing in our reality. For electricity, the equations clearly have a source, a point from which the electric field emanates. That source is the electric charge, a fundamental property of particles like the electron, which is a solitary negative charge. You can have a single, isolated electron, but for magnetism, Maxwell's equations contain no such solitary source term. In his framework, magnetic fields do not spring from a point, they always curl in loops. Every magnet, from a child's refrigerator magnet to the Earth itself, always has both a north and a south pole. Cut a bar magnet in half, and you do not get an isolated north and an isolated south. You get 2 smaller magnets, each with its own pair of poles. This is the first and most classical face of our monopole problem. The mathematics of our most successful theory of electromagnetism seems to quietly, but firmly, assert that isolated magnetic charges cannot exist. It was not a prediction of their existence, but rather a structural omission that suggested their impossibility. For over a century, this was simply accepted as a curious fact of nature, an asymmetry written into the cosmic rulebook. Why would the universe be so lopsided? Why would it grant us solitary electric charges in abundance, but forbid their magnetic counterparts? This question simmered in the background, a subtle itch for physicists who believed the cosmos preferred symmetry and elegance. The equations worked flawlessly without monopoles, so perhaps there was nothing to find. Yet, that very perfection felt, to some, like a clue. Could it be that Maxwell's equations were not stating a law, but were instead describing a universe from which something fundamental was already missing? The asymmetry was a silent scream in the mathematics, a hint that our understanding was incomplete, that a deeper truth was waiting to be uncovered. This quiet asymmetry would not remain unchallenged for long. The next great leap came not from tinkering with Maxwell's equations, but from a revolution that rewrote all the rules: quantum mechanics. In 1931, the brilliant and notoriously abstract physicist Paul Dirac asked a deceptively simple question. What if a magnetic monopole could exist within the strange, probabilistic world of quantum theory. He was not looking for one in a lab. He was exploring the mathematical landscape of possibility. And what he found was astonishing. Dirac discovered that quantum mechanics does not forbid magnetic monopoles. In fact, their existence would solve another deep mystery in one elegant stroke. He showed that if a single magnetic monopole with a magnetic charge we can call G were placed somewhere in the universe, the mathematics of quantum wave functions would demand a specific, locked relationship between that magnetic charge and all electric charges. The equation is simple yet profound. The product of the electric charge E and the magnetic charge G must be a multiple of a fundamental constant. This is Dirac's quantization condition. Think of it like a cosmic lock and key system. The existence of just one magnetic key, the monopole, forces every electric lock, every charged particle like the electron, to have a very specific, discrete size. It explains why electric charge in our universe is quantized, why we only ever see particles with exactly the same charge as the electron or simple fractions of it, never a continuous range of values. This was a monumental insight. A ghost we had never seen could explain a fundamental property of everything we do see, but Dirac's work came with a strange and visualizable twist, the infamous Dirac string. In his mathematical model, the magnetic field of the monopole did not radiate symmetrically like the electric field of an electron. Instead, it was as if all the magnetic flux was funneled out along an infinitely thin, invisible string, a singularity in the field that was mathematically necessary but physically undetectable. It was a mathematical artifact, a scar in the equations, but one with no measurable effect on particles. So Dirac handed physics a paradox wrapped in a promise. His quantum framework said monopoles could exist, and their existence would beautifully explain the quantization of electric charge. Yet, that same framework described them with an almost mythical feature, an invisible string tethering them to the fabric of space itself. The hunt was no longer just about a missing piece of Maxwell's symmetry. It was now a search for the key to one of nature's most precise numerical puzzles. If we could find just one of Dirac's monopoles, we would not just be cataloging a new particle. We would be uncovering the reason why the universe builds itself from discrete, identical building blocks. The ghost now had a purpose, and the mystery deepened from a curiosity into a necessity. Dirac's elegant idea was a whisper from the quantum world, but the next chapter in the monopole saga would come from a roar, the cataclysm of the Big Bang itself. As physics pushed deeper into the 20th century, a new and ambitious goal emerged: to unify the fundamental forces. We had successfully merged electricity and magnetism into electromagnetism, and later the weak nuclear force joined that union. But the strong nuclear force, which glues atomic nuclei together, remained stubbornly separate. Grand unified theories, known as GUTS, were the bold attempt to weave all three, the electromagnetic, weak, and strong forces, into a single, majestic mathematical tapestry. These theories describe a state of perfect symmetry that existed only in the unimaginably hot, dense first moments after the Big Bang, when the universe was a seething soup of pure energy. As the cosmos expanded and cooled, this symmetry broke like water freezing into ice crystals, and the three distinct forces we see today crystallized out. And here is where our ghost reappears, not as a subtle mathematical possibility, but as a concrete, inevitable prediction. In nearly every grand unified theory, the process of that cosmic symmetry breaking would have created defects in the fabric of spacetime itself, topological knots of energy that could not smooth themselves out. The magnetic monopole is one of these defects. According to GUTS, these are not delicate particles like the electron, they are primordial monsters. They would be unbelievably massive, perhaps as heavy as a single bacterium. To put that in perspective, a bacterium is about 10 trillion times heavier than a proton. They would carry a magnetic charge not just equal to Dirac's unit, but billions of times stronger. And most crucially, the theories predicted they should have been produced in staggering abundance in that early furnace, a relic population that should still be drifting through the cosmos today, as common as protons. This was no longer a philosophical maybe, it was a concrete prediction with a shocking consequence. If grand unified theories were correct, our universe should be absolutely flooded with these colossal magnetic fossils. They would be everywhere, in every liter of space, in the air we breathe, passing through our bodies constantly. Their immense mass and powerful charge would make them impossible to miss. We should be tripping over them, and yet we have never found a single one. This is the grand unified theory monopole problem, and it is a crisis of abundance. The universe seems to have cleaned its house with astonishing efficiency, leaving no trace of the messy aftermath the theories demand. The prediction of countless monopoles stands in direct, glaring conflict with the empty reality we observe. It means one of two unsettling things. Either our most ambitious theories about the universe's birth are fundamentally wrong, or something truly extraordinary happened in those first moments to sweep every last one of these magnetic giants away. The hunt for the ghost had just escalated from a search for a key particle to a desperate inquiry into the very first second of cosmic time. That prediction of a universe flooded with magnetic giants creates an immediate and catastrophic contradiction. If these massive monopoles were as abundant as grand unified theories suggest, they would not just be a curious component of the cosmos, they would be the cosmos. Their staggering collective mass would overwhelm everything else. The density of matter in the universe would be dominated by these relics, making the universe far heavier and denser than we observe. Galaxies, stars, planets, even the diffuse gas between galaxies, all the ordinary matter we can see and measure, would be a mere afterthought compared to the sheer gravitational weight of a sea of monopoles. Our universe would look nothing like the one we actually inhabit. It would be older, colder, and would have collapsed back on itself long ago under its own immense weight. This is not a minor discrepancy. It is a direct and glaring refutation of the theories by the reality they were meant to describe. The cosmological monopole problem presented physics with an impossible choice: abandon our most elegant theories of unification, or accept that our universe makes no sense. This crisis demanded a radical solution, and in the early 1980s, a young physicist named Alan Guth provided one. He proposed a breathtaking idea called cosmic inflation. The theory suggests that in the first fraction of a second after the Big Bang, the universe underwent a period of exponential, faster-than-light expansion. Space itself stretched at an incomprehensible rate, doubling in size over and over again in a tiny sliver of time. This was not an explosion of matter into space, but an explosive stretching of the fabric of space itself. And here is the key for our missing monopoles. This inflationary surge would have acted like a cosmic dilution pump. Any primordial monopoles produced in that initial fiery moment would have been scattered unimaginably far apart from one another. The density of these particles would have been diluted to virtually zero, as if taking a single drop of ink and spreading it across an ocean. Inflation elegantly sweeps the monopoles under the rug of the observable universe, explaining their profound absence while preserving the beautiful mathematics of grand unified theories. It tells us the monopoles are not gone, they are just so impossibly far away, separated by distances beyond our cosmic horizon, that we will never encounter one. So the hunt for a magnetic monopole transformed from a particle physics experiment into a test of cosmology itself. Finding even one would not just validate Dirac and the GUTS, it would pose a severe challenge to the inflationary model, throwing our understanding of the universe's first moments into fresh turmoil. The ghost's absence, it turns out, became the very evidence for one of the most important ideas in modern cosmology. This elegant solution of cosmic inflation, however, did not stop the search on Earth. If anything, it made the hunt more urgent and more creative. For decades, physicists have turned the entire planet into a trap, designing experiments of astonishing ingenuity to catch a ghost that may have been diluted to the edge of existence. The persistence of this search is a testament to what is at stake. Finding just one would be a discovery on par with the detection of the Higgs boson, a direct window into physics at energies a trillion times beyond what any particle collider can reach. So, how do you catch something that might not even be here? You look everywhere and in everything, with methods that range from the ultra-modern to the deeply ancient. At the forefront is the Mo-Edel experiment at CERN, the Large Hadron Collider's dedicated monopole and exotic particle detector. Its design is brilliantly simple. Instead of complex electronic sensors, Mo-Edel uses stacks of plastic sheets, similar to old-fashioned photographic film. The idea is that if a highly ionizing particle, like a massive monopole, streaks through, it would leave a permanent, microscopic damage trail in the plastic. These sheets are then chemically etched, making the tracks visible under a microscope. It is a passive, patient hunter, waiting for a monopole created in the high-energy collisions of the LHC, or, just maybe, one that has wandered in from deep space. But colliders are not the only venues. Other experiments listen for the unique signature a monopole would make. Imagine dropping a single, powerful magnet through a loop of superconducting wire. A moving magnetic charge would induce a persistent electric current in the superconductor, a current that would not decay, a permanent fingerprint of its passage. Detectors using this principle have scanned volumes of material for years, their supercold coils listening for the faint, eternal echo of a magnetic ghost. And then there are the time capsules. Some physicists search not in the present, but in the distant past, using the Earth itself as a detector. They examine ancient crystals of mica, formed deep underground over hundreds of millions of years. A heavy, slow-moving monopole passing through such a crystal would leave a trail of atomic dislocations, a fossilized scar locked in the mineral lattice. Similarly, samples of lunar rock, untouched by Earth's atmosphere and geological churn, are scrutinized for these ancient tracks. These experiments are archaeology on a subatomic scale, sifting through eons of silence for a single, catastrophic event. This global, multi-generational hunt, spanning from kilometers-deep mines to orbital satellites, reveals a profound truth. The monopole is more than a particle. It is a symbol of our relentless desire to test the furthest edges of our theories, to ask the universe a question so fundamental that the answer, whether yes or no, will reshape our understanding of reality itself. The search for a fundamental magnetic monopole may seem like a cosmic treasure hunt with an empty map, but in the last 2 decades, physicists have found something astonishing, a perfect mimic. This discovery did not come from a particle collider or a deep space probe, but from a strange, frozen world within certain crystals. in the realm of condensed matter physics, within exotic materials known as spin ices, our ghost has been conjured into a tangible, laboratory form. These are not the primordial monsters predicted by grand unified theories, but something called quasiparticles. Think of it like this. Imagine a crowded stadium doing a wave. The wave moves around the arena as a distinct, coherent entity, but it is not a physical object you can hold. It is an excitation, a pattern of collective behavior emerging from thousands of individual people. In a spin ice crystal, the atoms act like tiny bar magnets or spins arranged in a specific geometric frustration. They want to align in opposite directions to their neighbors, but the crystal's structure makes that impossible for all of them simultaneously, leaving them in a constant state of disordered tension, like a frustrated puzzle. Now, flip just one of these atomic magnets. To satisfy the rules of magnetism, this flip forces a chain reaction through the crystal lattice. The result is that two defects are created, one where the magnetic field lines appear to converge, and another where they appear to diverge. These defects behave in every measurable way like isolated north and south magnetic monopoles. They carry net magnetic charge. They interact with each other via a magnetic version of Coulomb's law, and they can even be pulled apart and moved independently through the crystal by applying a magnetic field. They are quasiparticles, emergent ghosts born from the collective dance of billions of atoms. This is more than just a clever analogy. It is a profound insight. It provides physicists with a sandbox universe, a controlled tabletop model where they can experimentally probe the physics of magnetic monopoles. They can study how these quasiparticles are created and annihilated, how they diffuse through a material, and how they respond to external forces. The discovery of monopole quasiparticles in spin ices is a breathtaking example of how nature can simulate the deepest secrets of particle physics in the frozen architecture of a crystal. It tells us that while the fundamental cosmic monopole remains elusive, its shadow walks among us, offering clues written not in the language of the Big Bang, but in the silent, ordered dance of atoms here on Earth. But what if our ghost is not a point at all? The Dirac monopole was a mathematical point charge with a strange string attached, an elegant but somewhat artificial construct. A deeper and more satisfying vision emerged in the 1970s from the work of Gerard T. Hooft and, independently, Alexander Polyakov. They discovered a monopole of breathtaking naturalness, one that emerges seamlessly from the fabric of a unified field. This is the T. Hooft-Polyakov monopole, and it is not a fundamental particle like an electron. Instead, think of it as a knot, a stable lump of energy in a field, what physicists call a soliton. A classic example of a soliton is a whirlpool in a river, a self-sustaining structure that maintains its shape as it moves, distinct from the flowing water around it. The T. Hooft-Polyakov monopole is a whirlpool in the fields that describe the early universe. It arises inevitably in certain grand unified theories when the symmetry of the hot, dense cosmos breaks. As the unified force field cools and settles into the distinct forces we know, it can develop regions where the field gets twisted into a stable, persistent configuration. This configuration has a net magnetic charge, but there is no singular point where that charge resides, and absolutely no Dirac string. The magnetic field emerges smoothly from the entire extended structure, like the magnetic field emanating from a tiny, perfect sphere that is itself made of pure field energy. This was a monumental shift in thinking. It showed that magnetic monopoles are not just quirky additions you can plug into a theory. They are robust, topological consequences of the unification process itself. In the landscapes of many grand unified models, they are as inevitable as wrinkles forming on a sheet as it cools. The 't Hooft-Polyakov monopole provided a concrete, mathematically beautiful blueprint for what these primordial relics might actually be, not points, but cosmic knots tied in the first moments of time. It transformed the monopole from a speculative possibility into a firm, theoretical prediction, making their continued absence in our detectors all the more perplexing and significant. The 't Hooft-Polyakov monopole gave our ghost a form, a knot of energy, but in the grand tapestry of the early universe, it may not have been alone. Some of the most fascinating theories suggest these magnetic knots were not isolated entities, but were tethered together by threads of pure energy, strung across the cosmos like beads on a necklace. These threads are known as cosmic strings, and they are among the most exotic relics imaginable. Picture a cosmic string not as a physical rope, but as a flaw, a crack in the fabric of space-time itself. Theorized to be thinner than a proton but stretching across light years, a single inch of such a string would weigh more than Mount Everest. They are lines of immense density and tension, remnants of phase transitions in the early universe, much like the cracks that form in ice as water freezes. In certain models, when the grand unified symmetry broke, it did not just create isolated monopoles. It spawned a chaotic network where monopoles and antimonopoles were born in pairs, connected by these infinitesimally thin, unbelievably strong strings. The early cosmos would have been a frenzied web of these vibrating filaments, each with a monstrous magnetic particle anchoring its ends. This was not a stable arrangement. The strings, under their own incredible tension, would have thrummed and oscillated violently. Like a rubber band snapping, a string could shrink, pulling its monopole and antimonopole endpoints together. When opposite magnetic charges meet, they annihilate in a catastrophic release of energy, converting their mass entirely into radiation. But here, the string itself adds to the fury, its entire immense energy also dissipating in a final, brilliant flash. The decay of this monopole string network would have been a symphony of destruction, flooding the infant universe with waves of energy. This could have been one of the most powerful engines in cosmic history. The sheer scale of this energy release might have stirred the primordial soup of matter, seeding the first tiny ripples in density that, over billions of years, would grow under gravity to become galaxies and clusters of galaxies. In this vision, our missing magnetic monopoles were not just passive relics, they were active architects, their violent demise alongside cosmic strings potentially helping to sculpt the large-scale structure of everything we see in the night sky. It is a breathtaking connection, linking the fate of a hypothetical subatomic particle to the majestic cosmic web of stars and galaxies. The silence in our detectors today, then, might be the quiet after a storm that built the universe. The violent decay of a cosmic string network leaves behind a profound silence, but could that silence itself be a clue to an even greater mystery? Our universe is filled with a ghost of a different kind, dark matter. We know it exists by its gravitational pull on galaxies, but for nearly a century, its true identity has remained utterly hidden. Could our two great cosmic phantoms be connected? This leads us to a thrilling modern speculation. Perhaps primordial magnetic monopoles are a component of dark matter itself. At first glance, the idea seems perfect. These relics from the Big Bang are massive, stable over cosmic timescales, and interact only very weakly with ordinary matter, primarily through gravity and their immense magnetic charge. They check many of the boxes for a dark matter candidate. They are dark, they are matter, and they would have been forged in the earliest moments of creation. But there are formidable challenges. The classic grand unified theory monopoles are predicted to be staggeringly heavy, each one weighing as much as a small bacterium. While that makes them massive, it also makes them incredibly rare if inflation diluted them properly. To account for the amount of dark matter we observe, you would need far fewer of these super-heavy objects than you would need lighter particles, like the hypothetical WIMP. But if they are too rare and too spread out, their collective gravity might not be enough to explain the dark matter's effects on the scale of galaxies. It is a delicate balancing act between mass, abundance, and distribution. To solve this puzzle, theorists have explored fascinating variants. One compelling idea comes from the Nobel laureate Julian Schwinger, who proposed the existence of dyons. A dyon is a hypothetical particle that carries both electric and magnetic charge. Think of it as a hybrid, combining the properties of an electron and a monopole into a single, more complex entity. Dyons could have different masses and interaction strengths than pure magnetic monopoles, potentially offering a better fit for the dark matter profile. They might cluster differently within galaxies or interact in subtle ways that leave a unique signature we could one day detect. The search for dark matter is already one of the greatest endeavors in science, employing deep underground labs, space telescopes, and vast particle detectors. If magnetic monopoles or dyons are part of that hidden cosmic budget, their discovery would achieve a monumental double victory, solving two of the universe's deepest mysteries with a single, profound observation. The ghost that haunts our equations of force might also be the invisible hand shaping the cosmos. The very existence of our galaxy's magnetic field tells us something profound about what is not there. While we chase the ghost of a monopole in laboratories, the cosmos itself has been conducting a far grander experiment for billions of years, and the results are written in the invisible lines of force that weave through interstellar space. Astronomers have observed that galaxies, and even the vast spaces between galaxy clusters, are threaded with large-scale magnetic fields. These fields are incredibly weak, millions of times fainter than a common refrigerator magnet, but they are immense in scale, stretching across tens of thousands of light years. Their persistence is a cosmic clue, one that the brilliant astrophysicist Eugene Parker, the man who gave his name to the solar wind, turned into a powerful detective tool in the 1980s. Parker realized that magnetic monopoles would be the ultimate saboteurs of these delicate cosmic fields. Here is why. A galactic magnetic field is a vast, diffuse structure, a slow, swirling current of force. Now, introduce a population of free magnetic charges into this system. Just as moving electric charges, like electrons in a wire, constitute an electric current, moving magnetic charges would constitute a magnetic current. Monopoles, drifting through the galaxy under the pull of its gravity and influenced by its magnetic field, would begin to move. They would essentially act like tiny, superconductive shunts. They would efficiently drain energy from the large-scale field, converting its organized power into random motion, and ultimately dissipating it as heat. It would be like poking countless microscopic holes in a vast, inflatable balloon. The structure would quickly collapse. Parker calculated that if the flux of monopoles, the number passing through a given area over time, were above a certain very low threshold, they would have short-circuited and destroyed these galactic magnetic fields long ago, on timescales far shorter than the age of the universe. The fact that we still observe these beautiful, faint magnetic structures spiraling through galaxies like our Milky Way means the monopole flux must be below that threshold. This ceiling is known as the Parker bound. It is not a detection, but a powerful exclusion. It tells us that monopoles cannot be so abundant that they disrupt the magnetic architecture of the cosmos. This astrophysical argument, drawn from the silent testimony of deep space, provides one of the tightest and most elegant constraints on how many of these magnetic phantoms could possibly be drifting through our neighborhood. The galaxy itself is a detector, and its enduring magnetic whisper tells us the ghost must be exceedingly rare. The Parker bound tells us monopoles must be rare, but it says nothing about what might happen if we ever actually found one. The consequences could be far stranger than just a new entry in the particle catalog. In the 1980s, two physicists, Vladimir Rubakov and Clifford Callan, made a prediction so startling it seems ripped from science fiction. They calculated that a grand unified theory monopole, drifting through ordinary matter, would not just pass by the atoms in its path, it would tear them apart from the inside. This is the Rubakov-Callan effect, the terrifying idea that a magnetic monopole could catalyze the decay of a proton. To understand why this is so shocking, you must first grasp the profound stability of the proton. In our everyday world, protons are eternal. The nucleus of every hydrogen atom is a single proton, and the atoms in your body have been cycling through the cosmos for billions of years. While some grand unified theories predict that protons should eventually decay, their calculated lifetime is unimaginably long, perhaps 10 to the power of 34 years or more, a timescale that makes the age of the universe seem like a blink. In practical terms, a proton is forever, but a GUT monopole changes all the rules. It is not just a magnet, it is a knot of the original unified field, a region where the distinctions between the strong nuclear force and the electroweak force begin to blur. When a proton, which is made of quarks bound by the strong force, comes near this exotic object, the monopole's core acts as a portal, a catalyst that allows the quarks to reconfigure in a way that is normally forbidden. In essence, the monopole provides a shortcut, a backdoor through which the proton can instantly fall apart, decaying into lighter particles like pions and positrons in a flash of energy. The monopole itself emerges unchanged, ready to destroy the next proton it encounters. It would be a cosmic wrecking ball on an atomic scale. This transforms the search for monopoles from a hunt for a passive relic into a hunt for a particle that leaves a trail of destruction. Imagine a single, invisible magnetic not passing through a tank of water or a block of iron. Along its path, protons in atomic nuclei would be spontaneously annihilating. Each decay would release a characteristic burst of radiation, a telltale signature. Early experiments, like the deep underground detectors built to search for proton decay itself, also listened for these telltale chains of events, hoping to catch a monopole in the act of its devastating passage. They looked for clusters of decays aligned in a track, a series of tiny explosions marking the ghost's deadly wake. No such trail has ever been found. Yet the prediction stands as one of the most dramatic in theoretical physics, a reminder that the missing monopole is not merely a curiosity. It is a potential key to processes that unravel the very fabric of stable matter, a phantom that could rewrite the rules of nuclear chemistry simply by being present. Its continued absence means our protons remain safe, for now, but the universe holds the blueprint for their destruction. The sheer destructive potential of a proton-decaying monopole makes its absence a cosmic relief, but it also sharpens a deeper question. Why are they so impossibly rare? We touched on the elegant solution of cosmic inflation earlier, but its role is so profound it deserves a deeper look, for it solves not one, but three of cosmology's greatest puzzles in a single, breathtaking stroke. Before inflation, the standard Big Bang model was plagued by mysteries. The horizon problem asked why the universe looks so uniform. Regions of space on opposite sides of the observable cosmos are so far apart that light, and thus any influence, could never have traveled between them since the beginning of time. Yet they have the same temperature and density as if they were once in perfect contact. The flatness problem was a question of geometry. Our universe appears remarkably flat, balanced precisely between an open, saddle-shaped geometry and a closed, spherical one. For it to be this flat today, its initial conditions at the Big Bang would have had to be fine-tuned to an unimaginable precision of 1 part in 10 to the power of 60. It would be like balancing a pencil on its tip for billions of years. And then, of course, there was the monopole problem, the prediction of a universe overwhelmingly dense with magnetic relics. Alan Gough's insight of cosmic inflation addressed all three with one mechanism. He proposed that a tiny fraction of a second after the initial singularity, a strange form of energy with negative pressure, akin to a repulsive gravity, caused the fabric of space itself to expand exponentially. The universe did not just grow, it ballooned by a factor of at least 10 to the power of 26, in perhaps as little as 10 to the power of negative 32 seconds. This hyper-expansion is the master key. For the horizon problem, it means that the entire observable universe was once a tiny, causally connected patch that was stretched to cosmic proportions, explaining its perfect uniformity. For the flatness problem, imagine taking a crumpled piece of paper, a highly curved surface, and stretching it to the size of a continent. Any local wrinkles or curvature become imperceptible, and the surface appears perfectly flat. Inflation did exactly that to the geometry of space-time, and for our magnetic ghosts, inflation was the ultimate cosmic dilution. Any primordial monopoles produced in that initial fiery instant were suddenly flung apart with such ferocity that their density plummeted to virtually zero. They were not destroyed, but scattered into the unimaginable vastness beyond our cosmic horizon. The observable universe became a single, monopole-free bubble within a much grander, perhaps infinite, cosmos that may still be teeming with them. In this view, inflation did not solve the monopole problem by proving the theories wrong. It solved it by hiding the evidence forever, sweeping the magnetic giants into a realm we can never access. This makes the ongoing search on Earth a fascinating gamble, a hunt for a particle that our best theory of the universe's birth says should be almost impossibly far away. The inflationary universe may have hidden the monopoles, but it did not erase them from the mathematical heart of our most ambitious theories. To find where they truly live, we must shrink our gaze from the vastness of the cosmos to the very fabric of reality itself, entering the realm of string theory. This is the great hope for a theory of everything, a framework where the fundamental constituents of the universe are not zero-dimensional points, but unimaginably tiny, vibrating loops of energy. In this elegant yet complex vision, the different particles we see, from electrons to quarks to photons, are simply different notes played on these microscopic strings. The forces between them, like gravity and electromagnetism, are the harmonies created by their interactions, and where do magnetic monopoles fit into this cosmic symphony? They emerge not as vibrating strings, but as something even more exotic, higher dimensional stages upon which the strings can play. These are called D-branes. Think of a string as a one-dimensional line. A D-brane, short for Dirichlet membrane, can be a two-dimensional sheet, a three-dimensional volume, or even higher dimensional surfaces, all existing within the theory's extra-spatial dimensions. In string theory, a magnetic monopole can be constructed as a D-brane that has been wrapped up or curled upon itself in a specific way within these hidden dimensions. The string and points can attach to these branes, and the brane's configuration determines the properties of the particle it represents. This gives physicists a powerful new toolkit. The old problem of the Dirac string, that artificial singularity, simply vanishes in this picture. The monopole is a smooth, stable, and natural object within the geometry of the theory. Furthermore, string theory provides a rich landscape of possibilities, predicting not just one type of monopole, but entire families with different masses, charges, and properties, all arising from different ways of wrapping these multidimensional membranes. It transforms the monopole from a singular ghost into a citizen of a vast and structured kingdom of potential particles. This mathematical depth is profound, but it also highlights a challenge. String theory's predictions are so tightly bound to the geometry of unseen dimensions that testing them directly seems, for now, nearly impossible. The monopole remains as theoretically elegant as ever, but its string-theoretic home is a palace built in dimensions we cannot perceive, a reminder that the most beautiful solutions in physics often point toward realities just beyond our current reach. The ghost leaves its mark not only through destruction, but through the most delicate of whispers, a subtlety written in the quantum phase of an electron. This brings us to one of the strangest and most beautiful effects in all of physics, the Aharonov-Bohm effect. Discovered in the 1950s, it revealed a truth that defies classical intuition. In our everyday world, a force must touch an object to affect it, but in the quantum realm, an electron can be influenced by a magnetic field even if it never, ever passes through it. The experiment is conceptually elegant. Imagine a beam of electrons split into two paths that travel around opposite sides of a long, thin solenoid, a perfect magnetic coil. Inside the solenoid is a strong magnetic field, but outside, the magnetic field is precisely zero. The electrons travel only through this field-free region. Yet, when the two beams recombine, their quantum interference pattern has shifted. The invisible magnetic potential, the abstract mathematical description of the field's source, has altered the electron's quantum phase along each path, as if the electron somehow knew about the hidden magnetism it never touched. It is a direct demonstration that the electromagnetic potential is a real, physical entity, not just a convenient calculation tool. Now, extend this idea to our elusive quarry. A magnetic monopole would create a very specific kind of magnetic potential throughout space. If you could send a beam of electrons on a closed path that encircles the location of a hidden monopole, the Aharonov-Bohm effect predicts that the electron's quantum phase would be shifted by an amount directly proportional to the monopole's magnetic charge. The path wouldn't need to go through any magnetic field, it just needs to loop around the source. This generalized Aharonov-Bohm effect provides a theoretical blueprint for an exquisitely sensitive, almost ethereal detection method. You wouldn't need to see the monopole or capture it. You would only need to detect the subtle, persistent twist it imprints on the quantum waves of passing particles. Building such a detector is a monumental challenge, requiring control over quantum systems at an extreme level, perhaps using ultra-cold atoms or superconducting circuits. But the principle offers a tantalizing possibility: to sense the ghost not by the trail of destruction it leaves, but by the silent, permanent warp it creates in the quantum landscape around it, a signature written in the fabric of possibility itself. The quantum whisper of the Aharonov-Bohm effect is a subtle signature, but the history of this search is punctuated by moments of thunderous, heart-stopping excitement. For decades, the field has been shadowed by tantalizing false positives and notorious hoaxes that remind us science is a profoundly human endeavor, driven as much by hope as by data. Perhaps the most famous of these near misses occurred on Valentine's Day, 1982, in a basement laboratory at Stanford University. Physicist Blas Cabrera had built an exquisitely sensitive detector, a small loop of superconducting wire cooled to near absolute zero. The principle was straightforward. If a magnetic monopole passed through the loop, it would induce a sudden, quantized jump in the electrical current, a perfect, unmistakable step. For months, the detector sat in silence. Then, on that February day, the pen on the chart recorder leapt. It recorded a signal that was, to Cabrera's astonishment, textbook perfect. The jump was exactly the size predicted for a Dirac monopole. The scientific world held its breath. Cabrera, cautious but understandably thrilled, published the single event, noting it was consistent with a magnetic monopole but stressing the need for confirmation. The paper ended with a simple, hopeful line: "This one event suggests the possible existence of a magnetic monopole." Laboratories around the globe scrambled to build similar detectors, hoping to catch a second glimpse. But that second event never came. The Valentine's Day monopole remained a solitary, haunting data point. Years of further observation by Cabrera and others yielded nothing. The perfect signal was likely caused by a subtle, unforeseen glitch, perhaps a tiny fragment of superconducting material breaking loose within the apparatus itself. The letdown was profound, a lesson in the cruel standards of proof. Science demands reproducibility, a signal that sings its song more than once. Yet, Cabrera's event was not a failure. It demonstrated that the experiments could reach the necessary sensitivity, and it burned the dream of discovery even brighter into the collective psyche of physics. Beyond such honest, agonizing near misses, the field has also weathered outright hoaxes. In the 1970s, a mysterious figure known only as the Mad Monopolist sent letters to physics departments, claiming to have isolated monopoles and even offering to sell them. Samples of supposed monopole-laden material were circulated, creating brief frenzies of analysis that always ended in the identification of ordinary magnetic minerals. These episodes, while frustrating, highlight the powerful allure of the prize. They serve as a constant reminder of the discipline and skepticism required, a necessary counterbalance to the wild hope that one day, a signal will not only be perfect, but will also repeat, heralding the end of a century-long chase and the start of a new chapter in understanding the universe. The silence of those early detectors speaks volumes, but it does not end the hunt. If nature will not deliver a monopole to us, perhaps we can summon one ourselves. This brings the quest into the most powerful laboratories ever built, particle accelerators like the Large Hadron Collider. The idea is audacious: to recreate, for a fleeting instant, the conditions of the early universe and forge a magnetic phantom with our own hands. The reality, however, is a story of staggering energy and stubborn absence. To create a true grand, unified theory monopole, the kind that is a knot in the unified field, we would need to concentrate an energy equivalent to 10 trillion times the mass of a proton into a single point. That energy scale, around 10 to the 16 giga-electronvolts, is a mountain compared to the hill the LHC can climb. Even at its phenomenal power, the LHC operates at energies roughly 1,000,000 times too low to reach that primordial summit. It is like trying to forge a star in a campfire. The intent is there, but the fundamental power is not. Yet, the dream is not entirely extinguished. Some theoretical extensions, models that live in the shadowlands beyond the standard model, predict lighter, more accessible magnetic objects. These might not be the primordial behemoths, but they could be siblings or cousins, particles with magnetic charge that could be produced at LHC energies. They carry names like electroweak monopoles or magnetic spin 1 particles. If they exist, a collision at the LHC could, in principle, pair-produce them, bringing a north and a south monopole into existence for a fraction of a second before they annihilate or escape. The trick is catching them, and here, their magnetic nature gives them a calling card unlike any other particle. A highly charged, massive particle moving through a detector would leave a trail of utter devastation. It would ionize atoms at an extraordinary rate, tearing electrons away with ferocious efficiency. In a detector like Mo-Edel or sections of Atlas and CMS, this would register as a track of intense, persistent ionization, a thick, unmistakable scar through the delicate electronic sensors. It would be a slow, heavy, penetrating signature, standing out starkly against the frenetic, light-speed spray of ordinary particles from a collision. Physicists have written algorithms specifically to search for these anomalous, heavily ionizing tracks. They have sifted through petabytes of collision data, looking for the unique fingerprint of a magnetic charge plowing through matter. So far, that fingerprint has not appeared. No confirmed event, no persistent trail has ever been recorded. This null result is itself a powerful piece of knowledge. It tightens the constraints, telling us that if these lighter monopoles exist, they must be even rarer or heavier than our most optimistic models predicted. The collider hunt continues, a high-stakes gamble where every upgrade in energy, every refinement in detection, brings us incrementally closer to either a historic creation or a deeper understanding of the barriers that protect our universe from its own hidden symmetries. The silence of our most powerful machines forces a question that transcends physics. If the universe refuses to yield a magnetic monopole, what does that tell us about the very nature of reality itself? For over a century, this ghost has been more than a particle. It has been a philosophical litmus test. Its existence or absence probes our deepest beliefs about how the cosmos is structured. At the heart of this lies a profound tension between two guiding principles, symmetry and simplicity. Our most beautiful theories, from Dirac's quantum vision to the grand unified models and even string theory, are built on a foundation of mathematical symmetry. They suggest the universe operates on elegant, balanced principles, and the magnetic monopole is a direct prediction of that elegance. It is the missing piece that would complete a perfect picture. To many physicists, its existence feels almost inevitable, a necessary consequence of a cosmos that values harmonious mathematical structure. Yet, nature has so far chosen a different path. The stubborn absence of monopoles whispers a different, humbler principle. Perhaps the universe values operational simplicity over abstract perfection. Maybe it found a way to be functional and stable without needing this particular kind of symmetry. This is the philosophical crux of the problem. If we never find a monopole, it forces a radical rethink. It means our most cherished theories, for all their beauty, might be leading us down a garden path of mathematical elegance that does not correspond to physical truth. We would have to question whether our hunger for symmetry is a reflection of the universe's design, or merely a preference of the human mind seeking order in the chaos. On the other hand, the discovery of just one magnetic monopole would be a triumph of a different kind. It would be a stunning validation that the universe does, in fact, speak the language of deep symmetry and mathematical inevitability. It would confirm that the human drive to find elegant, unified descriptions of nature is not a fantasy, but a genuine compass pointing toward reality's hidden blueprints. Finding a monopole would not just add a new particle to the catalog, it would affirm a philosophical stance that at its core, the cosmos is comprehensible because it is built on principles of profound and beautiful logic. So the ongoing search is more than an experiment, it is a dialogue with the universe. We are asking a fundamental question: are we projecting our love of symmetry onto the stars, or have the stars been whispering the equations of symmetry to us all along? The answer, locked within the ghost we chase, will define not just a chapter in physics, but our very conception of cosmic reason. This philosophical tension between symmetry and simplicity is mirrored in our most basic attempts to explain the monopole, often using the simplest of physical demonstrations. The classic analogy is the bar magnet. Anyone who has played with magnets knows you cannot isolate a single pole. If you take a magnet with a distinct north and south end and cut it in half, you do not get a solitary north and a solitary south. Instead, you create two smaller, complete magnets, each with its own pair of poles. This simple, tangible fact is a microcosm of the entire mystery. It shows us that within the magnetic systems we can touch and see, the monopole is forbidden, reinforcing the asymmetry Maxwell wrote into his equations. It is a hands-on lesson that nature seems to demand paired opposites in magnetism, a rule that feels arbitrary when compared to the freedom of electric charges. This everyday experiment is where the abstract problem takes root in our physical intuition, making the theoretical ghost feel even more strange and out of place. Yet, the human imagination is not bound by the limitations of iron and ceramic. The monopole's very elusiveness, its status as a missing piece, has made it a compelling fixture in science fiction and popular culture, where it can be reimagined as anything from a power source to a weapon. The most famous nod likely comes from Star Trek, where the term Dirac is used, a direct reference to Paul Dirac's work on antimatter and the quantum vacuum from which his monopole ideas emerge. In video games and other speculative fiction, monopoles often appear as exotic materials with impossible properties, capable of generating immense energy fields or destabilizing matter. These fictional portrayals, while taking creative license, capture the essential wonder of the idea. They reflect a broader cultural fascination with the holes in our scientific maps, the places where our knowledge ends and mystery begins. The magnetic monopole has transcended physics journals to become a symbol of the ultimate what if, a concept so potent it fuels stories about exploring the furthest edges of possibility. This cultural footprint is a testament to the problem's depth. It is not just an equation to be solved, but a story to be told, a blank space on the cosmic canvas that invites us to dream about what might be hiding in the shadows of reality. The dream of catching a magnetic ghost runs headlong into a wall of brutal engineering reality. To detect a monopole, you are not just looking for a needle in a haystack, you are looking for a single, specific needle in a haystack the size of a planet, and that needle might not even be there. The technical challenges are staggering, born directly from the particle's paradoxical nature. A grand, unified theory monopole would be a monster of mass and magnetic charge, yet it would be a phantom in its passage. Its immense mass, perhaps 10 trillion times that of a proton, means it would be slow-moving and carry tremendous momentum, making it deeply penetrating. It could slice through the entire Earth as if it were a wisp of fog, exiting the other side with barely a whisper of energy loss. Its primary interaction would not be through the strong or weak nuclear forces, but through its colossal magnetic charge. This creates a bizarre signature, a particle that barely notices atoms, yet when it does interact, it does so with ferocious, localized violence, ripping electrons away in a process called intense ionization. This combination of extreme penetration and sporadic, powerful bursts makes it a nightmare to trap. You cannot catch it in a bottle, and you cannot stop it with lead. You can only hope to witness its fleeting, devastating touch as it passes through. This forces detectors into a difficult compromise. They must be massive, presenting a large target volume to increase the infinitesimal chance of an encounter. They must be exquisitely sensitive, able to pick up that 1 in a trillion burst of ionization, and they must be patient, running not for days or months, but for years, even decades, accumulating what physicists call exposure. It is a game of cosmic statistics, where time and volume are your only allies against profound rarity. This is why some of the most promising searches have abandoned the idea of making monopoles altogether and instead look for them where they have always been, as natural relics wandering the cosmos. Experiments scan the heavens using satellites and high-altitude balloons to sift through cosmic rays, the rain of high-energy particles from deep space, hoping to find an anomalous, slow, heavily ionizing track that points back to a magnetic source. Others turn to the ultimate time capsules, ancient materials, dense, old minerals like mica, or samples of rock from the ocean floor or even the moon, have been sitting as passive detectors for millions, sometimes billions, of years. A single monopole passage through such a crystal would leave a permanent, fossilized trail of atomic damage, a scar frozen in geological time. By chemically etching these materials, scientists can search for these etched tracks under a microscope, performing archaeology on a subatomic scale. In this light, our most powerful particle accelerators, for all their glory, may be the wrong tool for this particular job. They create a frantic, microscopic firework display of energy, but the monopoles we seek are not sparks. They are glaciers, primordial relics from a colder, more violent age. The real hunt is not about creating the ghost, but about finding where it has been hiding all along, in the silent depths of space or locked within the ancient heart of a stone. To grasp how these magnetic giants could have been forged, we must journey back to the first unimaginable sliver of a second after the Big Bang. The newborn universe was not a place of distinct particles and forces as we know them, but a seething, ultra-hot plasma of pure energy, a state of perfect symmetry. In this primordial furnace, the fundamental forces we recognize today, electromagnetism and the strong and weak nuclear forces, were fused into a single, unified superforce. There was no distinction between a magnet and a glue that binds atomic nuclei. They were one and the same, but this perfection could not last. As the cosmos expanded at a furious rate, it cooled. And just as steam condenses into water or water freezes into ice, the universe underwent dramatic phase transitions. The unified force field began to crystallize, breaking its perfect symmetry as it settled into the lower energy states that define our reality. This process was not smooth and uniform. Think of a pond freezing on a cold night. As the water turns to ice, the crystalline structure forms in different patches simultaneously. When these growing patches of ice meet, their orientations don't always match up perfectly. Where they collide, lines of stress and imperfections form, cracks and flaws locked into the structure. In the freezing early universe, the crystal that was forming was the very fabric of space-time and the forces within it. As different regions of the cooling cosmos chose slightly different orientations for the emerging force fields, they created boundaries, knots of trapped energy where the original, symmetric state persisted in a twisted form. These are topological defects, and a magnetic monopole is one specific, stable type of these defects. It is a point-like knot, a relic bubble of that earlier, more symmetric universe that got pinned in place as everything else changed around it. According to this mechanism, monopoles weren't just possible, they were inevitable byproducts of cosmic cooling, like frost heaves on a freezing road. The mathematics of grand unified theories suggests they would have been produced in staggering numbers, perhaps one defect for every phase transition region in the early cosmos. This production mechanism is why their predicted abundance was so catastrophic, and why their profound absence forced physicists to invent the concept of cosmic inflation to explain where they all went. The ghost, it seems, was born in the cracks between worlds, frozen into existence in the first moments of creation. The relentless hunt for a monopole forces us to confront a radical possibility. What if our most elegant theories are simply pointing in the wrong direction? The 21st face of this problem asks whether we can build a universe without the ghost, constructing grand unified models that elegantly sidestep the monopole prediction entirely. This is not about hiding the particle with inflation, but about changing the blueprint of reality so it never appears in the first place. The key lies in the delicate choreography of symmetry breaking. In standard GUTS, as the hot, symmetric universe cools, it is forced to choose a specific, lower energy state, like a ball rolling into one particular valley in a mountainous landscape. That transition inevitably creates topological defects, the magnetic knots we call monopoles. But what if the landscape is different? Some alternative theories propose a smoother descent. Imagine the ball rolling down not into a single, deep valley, but onto a vast, gently sloping plateau. The symmetry breaks, but it does so in a continuous, gradual way that leaves no sharp boundaries, no frozen cracks in spacetime. In such a model, monopoles simply do not form, they are not a feature of the cosmic story. Other approaches, like prion models or composite models, suggest that the forces we see are not fundamental, but emerge from the interactions of more basic building blocks. In these frameworks, the concept of a fundamental magnetic charge might not even make sense, rendering the whole quest for a Dirac-style monopole moot. This leads to a profound philosophical question. Is designing a theory to avoid the monopole problem a clever refinement, or is it a form of cheating? For some physicists, it feels like moving the goalposts. The beauty and predictive power of the original grand unified theories came from their rigid mathematical structure, a structure that demanded monopoles. To alter that structure specifically to remove an inconvenient prediction can seem ad hoc, like trimming the puzzle piece to fit the hole rather than searching for the right piece. Yet, science advances not just by confirming predictions, but by falsifying them. The stark absence of monopoles is a clear signal from nature that something in the standard GUT picture is incorrect. Refining our models in response to this negative evidence is the very essence of the scientific method. It is how we listen to the universe and correct our course. Perhaps the true path to unification does not lie in the valleys that spawn monsters, but on the smooth plains that promise a cleaner, quieter dawn. The ghost's greatest legacy may not be its discovery, but the way its absence forces us to imagine entirely new architectures for reality. The sheer theoretical weight of the monopole makes its practical potential almost a fever dream, yet it is a dream worth exploring. If we ever captured and tamed even a single one of these magnetic ghosts, the technological landscape of our civilization would shatter. The key lies in their unique property, the magnetic charge. In our world, we store energy chemically in batteries or kinetically in flywheels. But imagine a magnetic battery. A single, stable monopole sitting inside a perfectly engineered coil would represent a reservoir of pure magnetic flux. Because magnetic fields can do work, this setup could, in theory, release energy with an efficiency and density that makes our best lithium-ion cells look like damp firewood. The energy density could be astronomical, powering a city for centuries or a spacecraft for millennia on the charge of a single, pinhead-sized cell. This speculation extends to propulsion. A spacecraft equipped with a monopole could, in principle, interact with the magnetic fields of planets and stars, not by expelling reaction mass like a rocket, but by essentially sailing on the galactic magnetic field lines, achieving acceleration without fuel. It would be a true mag sail, a concept straight from science fiction that would open the solar system. Of course, this is all wild, blue sky speculation, bordering on fantasy. The engineering challenges would be unimaginable, containing something with a magnetic charge billions of times stronger than anything we have ever handled, preventing it from annihilating all circuitry or catalyzing proton decay in its housing. But that is precisely the point of this thought experiment. The discovery of a magnetic monopole would not merely answer a century-old physics question. It would ignite a new age of technological possibility. It would signal that the universe contains tools and principles we have not yet dared to dream of, turning the ghost from a phantom of theory into a key to a future we can barely envision. The dream of a monopole-powered starship exists in a distant future, but the drive to find one is rooted in a very human present. This brings us to a quieter, more personal dimension of the mystery, the psychology of the hunt itself. For generations of physicists, the magnetic monopole has been more than a particle. It has become a symbol of pure scientific aspiration. Its pursuit shares a profound kinship with other great quests of modern science, like the decades-long search for the Higgs boson or the patient listening for gravitational waves. These are endeavors that demand immense resources, staggering patience, and a willingness to follow a theoretical map that might lead to nothing at all. Teams of brilliant minds dedicate entire careers to designing ever more sensitive experiments, knowing full well they may retire without ever seeing the signal they were built to find. The Large Hadron Collider cost billions to construct and required a global collaboration of thousands. The LIGO Observatory listened in silence for years before catching the first whisper of colliding black holes. The monopole search, while less centralized, carries the same weight of uncertainty. It is a gamble driven not by promise of profit or immediate application, but by a deep, collective curiosity, a need to see if the universe's most elegant equations are telling the truth. There is a powerful human desire to complete a picture, to find the missing piece that makes a beautiful theory whole. This psychological drive is what sustains a community of researchers who return to their labs, their ancient rock samples, and their data streams year after year. They are not just testing a hypothesis, they are answering a call from the mathematics itself, a whisper that says something fundamental is waiting to be found. In a world often focused on practical outcomes, this relentless, curiosity-fueled pursuit is a testament to a different kind of value, the value of knowing simply for the sake of knowing. The silence from the detectors is not a deterrent, it is a challenge, and the human spirit has never been good at ignoring a challenge written into the fabric of reality. That deep human drive to find a missing piece connects to the final, breathtaking scope of the problem. The magnetic monopole is not an isolated puzzle. It is a thread woven tightly into the grand tapestry of physics' greatest mysteries. Its existence or absence speaks directly to questions that define the very structure of our reality. Consider the first moments of creation, when the universe forged matter. One of the most profound imbalances we live with is the fact that we are here at all. During the Big Bang, matter and antimatter should have been produced in equal amounts, destined to annihilate each other completely, leaving behind a universe of pure, empty light. Yet somehow, a tiny excess of matter survived, one extra particle for every billion annihilations, and that tiny excess built every star, planet, and person. This is the mystery of baryogenesis. Could magnetic monopoles have been the architects of this survival? Some theories suggest that in their interactions, particularly if they are the hybrid particles known as dyons, they could have violated the symmetry between matter and antimatter in a unique way. As these primordial relics moved through the hot, early plasma, their unique properties might have tipped the scales, creating the critical surplus of protons and neutrons that made our material universe possible. In this scenario, the ghost we cannot find may be the very reason we are here to look for it. Then there is the hierarchy problem, a question of staggering scale. Gravity is unimaginably weaker than the other fundamental forces. The magnet on your refrigerator, a product of the electromagnetic force, can defeat the gravitational pull of the entire Earth. This disparity, a factor of about 10 to the power of 36, seems absurd and unnatural in our current theories. It begs for an explanation. Some speculative ideas in particle physics propose that this weakness is not fundamental, but an emergent effect. And within these frameworks, the properties of particles like magnetic monopoles, their immense masses and unique couplings, could play a role in stabilizing this vast gulf between forces. Their predicted mass scale sits intriguingly close to the energy where gravity is expected to become strong, acting as a kind of bridge or landmark in the landscape of physics. The monopole problem, therefore, is not a solitary island. It is a central junction, connecting to the mystery of our own existence in a matter-filled cosmos and to the perplexing, foundational weakness of gravity that shapes the universe's architecture. Solving it would not just fill one blank space, it would send shockwaves through our understanding of everything, illuminating connections between puzzles we have long seen as separate. The ghost's shadow touches every corner of the map. The search for our magnetic ghost is far from over, it is simply evolving. The next generation of experiments will not just be bigger, they will be smarter, weaving together new technologies and ancient landscapes in a final, all-encompassing sweep. One audacious idea transforms our entire planet into a detector. Imagine using the global network of seismic sensors, the same instruments that listen for earthquakes, to hunt for a subatomic relic. The concept is breathtaking in its scale. A super-heavy magnetic monopole, drawn by Earth's gravity, could eventually settle toward the planet's core. As it plummets through the dense mantle and outer core, its immense mass and momentum would generate a tiny, distinctive seismic ripple, a whisper of a tremor unlike any natural quake. By analyzing patterns from thousands of seismic stations worldwide, physicists could, in theory, triangulate the passage of such an object, using the Earth itself as a gargantuan, geological-scale particle track. Similarly, the Moon, with its dead, seismically quiet interior, offers an even cleaner slate. Future lunar bases could deploy networks of sensors specifically designed to listen for the telltale thump of a monopole coming to rest, turning our celestial neighbor into a pristine, billion-year-old trap. Beyond planetary bodies, the hunt extends to the magnetic fields that cradle them. Jupiter, with its ferocious magnetic field 20,000 times stronger than Earth's, could act as a natural concentrator. Monopoles, if they drift through the solar system, would be drawn into these planetary magnetic traps, spiraling along the field lines and accumulating over eons. Future space probes equipped with specialized detectors could fly through the radiation belts of Jupiter or Saturn, not to study the planets, but to sift through their captured cosmic dust, hoping to find a single, anomalous magnetic signature adrift in the storm. Back on Earth, laboratory techniques are reaching new frontiers of sensitivity. Quantum sensors, devices that exploit the bizarre rules of the quantum world to measure forces with impossible precision, are coming of age. Imagine a tiny, levitating superconducting sphere, its quantum state exquisitely sensitive to the slightest magnetic disturbance. A single monopole passing within kilometers could, in theory, nudge this quantum needle, registering its presence without ever making direct contact. Other proposals involve using dense clouds of ultra-cold atoms, held in magnetic traps, whose collective behavior would shift in the presence of a nearby magnetic charge. These are not brute force experiments. They are exercises in listening to the universe's quietest hum. The theoretical front is equally vibrant. As we refine our understanding of the early universe and the mathematics of string theory, new predictions emerge about where monopoles might hide or what subtle signatures they might leave on the cosmic microwave background, the afterglow of the Big Bang. The future of this century-long quest is a mosaic of scale, from the quantum vibrations of a single atom to the seismic heartbeat of an entire world. It is a testament to human ingenuity, a promise that we will keep looking, keep listening, and keep asking the cosmos if it has been keeping a magnificent secret from us all this time. This century-long chase through equations and experiments, from Dirac's elegant mathematics to the explosive vision of cosmic inflation, has revealed a truth far greater than any single particle. The magnetic monopole is a mirror. It reflects our deepest hopes for a universe built on symmetry and elegance, and it mercilessly exposes the cracks in our most beautiful theories when they clash with silent reality. We have followed its ghost through 25 distinct facets, seeing it as a missing piece of Maxwell's puzzle, a quantum key to charge, a cosmic relic diluted by inflation, and even a tangible quasi-particle dancing within frozen crystals. We have watched it threaten to decay protons, potentially seed galaxies, and whisper its presence through quantum phases. Each perspective is a different lens on the same profound mystery, a question that has shaped modern physics. To finally resolve this epic quest, whether by capturing the ghost in a detector or by rewriting the theoretical maps that predict it, would not merely fill a gap in a textbook. It would be a monumental leap, a definitive answer to a question that has probed the universe's very character. It would tell us if our hunger for mathematical beauty is a genuine compass or a magnificent illusion. So we turn the question to you, the fellow traveler on this journey. After seeing the scale of the search and the weight of the silence, where does your intuition lie? Do you believe these magnetic phantoms are out there, waiting in the depths of space or the heart of some future collision? Or is nature's persistent quiet a clear signal that we must imagine a cosmos of a different, perhaps even more fascinating, design? Let us know your thoughts in the comments below. If you enjoyed this deep dive into one of physics' greatest enduring mysteries, be sure to like this video and subscribe for more journeys to the edges of our understanding. The conversation, just like the search, continues.